Welcome to the last Q&A session of ViViMaT. Valentin Salinas, Stefan Peeters, and Chia-Jui Hsu are first grilled about their work and then muse on the future of ZDDP research. Coatings is a peer-reviewed journal of coatings and surface engineering published online by MDPI on a monthly basis.
Maybe to continue with Valentin, that was also a very rich presentation. First of all, I would like to congratulate you on the paper, actually Nature paper. So just to cite Stefan, I think we have something in common with Stefan, or I have something in common with Stefan. We have not yet achieved a Nature paper, at least with Nature in the title. So well done, great achievement. And when I was watching your presentation, yeah, I think this is really worth a little applause. When I was watching your presentation, actually, I understand why, because it's so full of information and so rich of different aspects. So great, cool stuff. But we have first to return to the ice cream again. I'm sorry, Stefan started the game, so we have to continue. So what's your favorite?
Probably cassis and lemon.
Aha, okay, always something new, really great. So coming now from some tasty stuff to some maybe from the chemistry point of view, untasty stuff. I think sulfur is not so tasty. But what I learned is actually when you were studying this ACH and AC and different TAC coatings with different hardness, you reported on the fact that when you have really hard TAC coatings, that actually they start wearing off faster, and it was not so good in performance anymore than the softer ones. I was asking myself, is there any kind of an optimum hardness that you could set or predict where you have the best from both sides? You know what I mean?
Mm-hmm. Yeah, so in our case, we tested 5 different DLCs. And the optimal DLC was a tetrahedral amorphous carbon that had a hardness of 50 gigapascals. It was the optimal because the friction coefficient was the lowest, 0.02, and it did not exhibit wear. So this was the best one. So we call it like a moderate hard TAC.
Okay, and from the theoretical point of view, if you would try to comment on that, I mean, this is now a value. It can be just by accident that you found 50 is the best one. But could you think of, is there any optimum, and why is this optimum? I mean, you presented in the very end a kind of a model where I will have another question later on. But how do you see that from the theoretical point of view?
Yes, so it doesn't only depend on the hardness. It also depends on the composition of the DLC, so the hydrogen content, and also the surface topography. So in general, what we observe is that we need a DLC that is basically a combination of 2 parameters, the elastic modulus and the slope of the RMS height. And the combination of these 2 parameters will determine the local contact pressure at the asperity levels. So in the presence of CDDP lubrication, we need these pressures to be lower than 4 or 5 gigapascals. Because higher than these values, then we have defragmentation, decomposition of the CDDP molecule, and then we have this sulfur diffusion problem. So we need, first of all, to keep the local pressures low, so below like 4 gigapascals or something like this. And then the question that we still haven't answered fully is why the friction coefficient is lower for a hard TAC than a softer AC or ACH. So we still need a little bit more of experimental proof to explain why this happens. But at least we know that for sure we have to prevent wear. And to prevent wear, we need low local pressures.
Okay, I got a bit confused in not because of your presentation. I got confused by myself when I tried to understand some of the things that also my friend Ray, I will ask him a little bit later on, who's watching now. When you study surfaces, metallic surfaces under ZDDP additivation, we know that actually when I talked to you, Spikes, he said, okay, you can see, for example, on iron materials or harder materials, you see that this tribofilm forms. If you go to a softer material, maybe aluminium or something else, the effect is not that clear, or you do not see it at all. And he said, okay, you need a certain hardness. And now there is a kind of a conflict, because what you presented is if the hardness is too high, in your case, it's detrimental. On the other hand, if you just look at the metallic surface and you have a ZTB additivation, it requires a certain hardness, of course, to get the tribofilm formed. So is this also kind of a random correlation, or is there a kind of a master plan behind, or some more general rule behind, or is that all too far-fetched now?
No, the situation is actually quite opposite from, or very different from metallic surfaces, which are very reactive. And you have, I think in one publication of Hugh Spikes, he has like an order of metals which are more reactive with CDDP. But in the case of DLCs, they are very inert surfaces. They only contain carbon, basically. So in this case, they are much less reactive with the CDDP molecule. And for DLCs, basically the soft DLCs allow for cross-linking and stacking of CDP molecules, while very hard DLCs will completely decompose the molecule, and so it will not form a tribofilm.
Okay, yeah, cool. I like that. So it's a pretty good work. So thanks, Valentin, so far, and I will have another couple of questions then at a later stage today.
All right.
So Stefan, your turn again.
Well, also, Valentin, for me, congratulations to your paper. I'm a bit jealous, but also because, you know, the author list just reads like some sort of a who is who. I think I'm going to ask Stefan something now, if that's okay. So first of all, ice cream.
Yes, this is the toughest question of the day, probably. I will go with chocolate to go with a classic.
Okay. Now, second, moving to more scientific parts. Okay, so whenever somebody talks about DFT, and also when I was reviewing your paper, it's like, you know, the head seems to bubble over because there's just so much in there. I have collaborated with people that have done DFT, and they've explained a couple of things to me. I've never seen the term SOMO. So I've heard of HOMO, the highest occupied molecular orbital, right? And LUMO is the lowest unoccupied one. Can you expand, first of all, explain to me what SOMO means? And second, can you expand a little bit on the, let's say, the utility of these frontier molecular orbitals? They're wonderful representations. Is that to show where the reactive sites are? What can you read from that, and how can you make that into usable information for, you know, the results?
Sure.
Could you expand on that a little?
Yeah, of course. Well, SOMO is the acronym of singly occupied molecular orbital, because basically HOMO and LUMO are very common, and because most of the molecules and the substances have closed shells. So you have an orbital which is completely filled with 2 electrons, or otherwise is completely empty. But SOMO is a way just to call orbitals which are occupied only by 1 electron. So it is not completely filled and is not completely empty. So so what we studied was a radical cation, and we had this 1 electron. It is just a proper way to call the frontier orbital. And concerning the frontier molecular orbitals, well, actually we are studying the additives, the molecules from scratch, let's say, starting from isolated conditions, and then we move to the interactions with the substrates. Our idea is to try and to find an explanation for the reactivity of these additives by looking at the electronic properties. Of course, if orbitals, well, in chemistry, you could have a very big debate on the nature of the orbitals, on the basis set, on what they represent. But in general, if you look at this nice picture with the blobs, let's say, they represent the probability where to find electrons. So in most cases, you can also say that electrons may be localized in some part with respect to some other parts. And so if you put additives molecules or other lubricants in contact with the with surfaces, maybe you can also say that this is the effect of a particular portion of the molecule, so of course it can also give you information on the probability that the electrons of the molecule can jump to the surface or vice versa.
All right, yeah, thank you very much. So basically, I mean, could we boil it down to we're trying to find the interesting regions of the molecules where it's a tool to find where it's most likely that something interesting will happen. And you as a DFT person will then basically design your systems in a way that you probe those interesting areas and those most interesting, promising constellations. Can we sort of, yeah?
Yes, because for the molecules I studied, which was MODTC, and I'm starting to study ZDDP right now, the first steps of their activation concern the breaking of some bonds and the formation of new bonds. And these bonds breaking and forming are just electrons that jump from one place to the other. So it is quite important to see where this transformation occur. And so maybe, hopefully, we can predict some beneficial aspects of the molecules and some other aspects that hinder the decomposition.
Yeah, cool. Thank you very much. I think we're going to have some other questions later, and if we can manage, it would be great if we could have a little bit of a discussion, maybe between Ray, you, and Valentin about. I would imagine maybe modeling of ZDDP and how can that be improved, but maybe a little bit later. Yeah, thank you very much. Over to you, Carsten.
Yeah, Ray. First of all, yes. Great presentation. Second, again, in your case, a bit difficult because, yeah, we also know each other for many years, and it was not so easy for me to think of some particular questions. But Ray, there's one thing I really want to focus on again, because I guess that is also for the community pretty interesting. But of course, as you know, that's the game. Before we start with the scientific question, your ice cream, please.
Okay. Peanut butter maybe, but it's very hard to find here in Vienna. So I would choose caramel. It's similar.
Okay, so we had already salty caramel before from Stefan, so very good. Well, you worked a lot in the past years with surface texturing by laser. And interestingly, we found out together that you know, sometimes people say, yeah, when you texture a surface and you're looking at machine elements, it might have detrimental effects on fatigue resistance. And in the last paper published in journal Friction, you clearly showed that this must not be the case. So we saw actually an increase in fatigue resistance by a factor of 3. And maybe you could give just the people listening now and also the community a kind of an easy explanation or the idea behind what is the reason for this increase in the fatigue resistance, because it doesn't seem so logic from the first point of view. But that's what we measured, right? So do you have a kind of an easygoing or fast explanation what could be the reason for this increase in fatigue resistance, even after surface texturing of the component?
Yeah, so it's a very a common question, because when talking about laser surface texturing, because we change the surface, and normally it's thinking about the increase of contact pressure, and that's true. And the purpose actually to have this surface texturing is to create these surface pockets that we can store some lubricant inside, and also it can change the hydrodynamic pressure that can be induced a little bit. But if we come back to the theory that in the boundary lubrication, it's actually that the direct contact will happen. So the asperity contact will get stronger and stronger. And in that case, the only way to prevent the wear is to have this protection layer. And actually, I mean, to be honest, it's a little bit lucky because by having the surface texturing, the surface has to be, be well designed, and also different type of the sliding speed or the geometry will change the reaction. And we are lucky that we in our that the candidates, one of it has a very good reaction that actually it induced this protection layer. Actually, it's the ZDDP. So this protection layer actually protect the surface because it prevent the direct contact and then stop this harmful damage chain actually. So this is my answer is like that because of the increase of the pressure is actually in a good range to generate a ZDDP protection layer. So that's in this case, we can protect actually the machine element. But if you ask me about like how to design or have a general idea to protect machine elements, I have to say it has to be well designed and also with some experience to try and errors, then we can find a more customized parameters to do the laser texture. Yes.
Mm-hmm. Yeah, and as we started to ask you pretty late, so it took 1 hour to ask you a first question, so I give you another one.
Yes.
By the laser in general, for most of the people listening and maybe not working that intensively in the field of laser surface texturing, it's not just a tool where you can create well-defined topographies and material surfaces. It's also basically a heat source, and by putting the heat source on the metallic surface, you also change surface chemistry. You may melt and resolidify the material. Have you seen in your studies any influence after the surface texturing on the ZDDP tribofilm formation, because the oxide situation, the scale thickness, also the stoichiometry of the oxides is different from the original state? Have you observed any kind of difference related to that after the surface texturing?
Oh yes, exactly. The surface actually it's in a good agreement with our previous study. So it has a oxide layer on top, and also the hardness increased a little bit. But in the end, is as I said, what is the key factor is still the generation of this protection layer. So in that case, it is not having so much influence, to be honest. But we also check, yes, of course, before having this frictional test, we also check the cross section and also see the hardness of it. It has a good agreement with previous study, but it is not influencing the frictional results.
Okay. Yeah, thanks, Ray, for the moment. Yeah, actually, Valentin, I guess after your Nature publication, you stopped your scientific career, right? So it's time to get retired. No, joking. So Valentin, I was actually when I was listening to the final part of your presentation, and I was also reading Stefan's question. I also have the same feeling, the same question. So when you presented in the very end this picture where you say, okay, if you have a softer TAC coating, so you are able to somehow partially decompose the ZDDP and then to create a tribofilm that has, you mentioned 20 nanometers, right? In that range on top of the surface. And I remember that below that you said, okay, when we then have a hard TAC coating, you somehow have chemical mixing, and you mix that all up and you have a kind of a ACS composition-wise compound that is weaker than that. So is it about weakening effects, or this, let's say, Stefan formulated in a way, the claim is if it's the cold welding, the CC bonding that allows the sulfur to diffuse into the layer, making it weaker, question mark. Did you see from the simulations how the mechanism of the reaction pathway was for the sulfur? So maybe you can have a quick comment on this.
Yes. So in the top part of the drawing, it's not only soft DLCs, but it's also smooth DLCs. So both the mechanical properties and the surface topography, they are important, right? To determine local pressures at asperities. And then for the cold welding, there are a few conditions that have to be met so that cold welding occurs. First, you need pressures that are higher than 5 gigapascals at contact asperities. And this is only the case for the hardest DLCs. And the second is that the DLCs have to be hydrogen-free, because even at very high pressures, if there is hydrogen in the DLC, then cold welding does not occur.
Mm-hmm.
And so cold welding will lead to very high pressures and defragmentation of the CDP molecule. And so we studied the bond breaking of the molecule and bond forming with the DLC. So sulfur is the first atom to be released from the molecule, the first one to break. So with cold welding, what you have is, and also with the shear stress and the temperature, which is also an important factor, is that you have increased mobility of the atoms and the CDP fragments. So in cold welding, you're going to provoke a diffusion of these atoms and molecules into the DLC. And so to get this chemical mixing. And what we saw by the simulations and also by different papers that measure this experimentally is that the sulfur is going to amorphize, is going to provoke a structural transformation from the amorphous carbon to like a graphitic carbon. And we also show some TM images where we see like these rich graphite carbon structures, even some like onion structures. So this material is much, much weaker than the original DLC. And this is why then we are observing wear.
Okay, yeah, cool. Very good, very good. I was wondering a little bit in which direction that goes. And yeah, as you mentioned, of course, it's also about the roughness. So other factors, of course, play an important role. Thanks for that, Valentin. I think we will have a final comment today also with Stefan together, Stefan Peeters and others who are in this club of ZADP people. As Stefan Eder already said, Quo Vadis ZADP for the future. Maybe coming to a last quick question, as we already stated before, we have this club of gentlemen dealing with ZADP, and I would like to ask a question about this. I call it Quo Vadis. So which are the next big steps in ZADP research? And as Stefan Peeters also had for a longer time, no question from our side. Maybe Stefan can comment first on where he sees the progress or the direction for the ZADP research or open questions still related to ZADP research. And then we can go on with Valentin and Ray and others who want to comment on that. But Stefan, please, you're the first one to comment on it.
Thanks. Well, this is a very nice question, and as we are starting to study ZADP very recently, I will give an answer by stepping on the shoulders of the giants before me. But from what I see, ZADP is very well studied. There is a lot of knowledge concerning ZADP by itself and its interaction for steel. And there is need to find more sustainable additives. So in a way, there's the possibility to replace ZADP, to find additives that work as well as ZADP, which is currently, I think, the best one. And but also to describe the interactions of ZADP with different substrates, as it has been shown very successfully the interaction with DLC, but also it is quite interesting to see what happens with the lightweight alloys. I just briefly showed something in my presentation because lightweight alloys can be very useful to reduce the weight of cars, of course. And there is not so much about this. So probably it could be very interesting to expand on this topic and to play a little bit with the substrate. For example, by texturing and patterning as the presentation by Ray. And so this is my idea, but of course, there's plenty more to do, I think, in this topic.
Very good, Stefan. Yeah, these are all important points that you raised. Thank you very much. And then maybe Valentin, a quick comment on where do you see ZDDP in the future and research in that direction?
Yes, so I agree with Stefan that CDDP has been studied for many decades now, and its reaction mechanisms and anti-wear process are very well known for steel surfaces. And it's true that we would like to use greener or less polluting additives, but so far we cannot find one. It's too good CDDP to be replaced. So specifically in internal combustion engines, now we're starting, well, for more than 10 years, we're starting to coat the steel surfaces with DLCs, right? So that was the motivation behind our specific study, because we knew how it reacted with steel, but we didn't know how it behaved with other materials. So I think that by finding new materials, we are going to discover more things that we don't know about CDDP and its interactions with other things. And also, well, I've heard comments in different conferences. They say, well, now everyone's going to drive electric cars, so you won't need CDDP in the internal combustion engine. But I think that we're still a lot of decades away from this happening, right? So I still think that CDDP is very relevant today. And not only in internal combustion engines, there's also some of our colleagues are working with the lubrication of aeolians, these are wind turbines. So I think it's still a very interesting and very relevant topic.
Mm-hmm. Yeah, thank you very much. That is excellent. Ray, any additional comment on that? What the two colleagues said before?
Yeah, I'm more like an experimental guy, so I'm not very sure about the simulation, but I have a feeling that recently the interaction between the surface and the surfer itself is getting more, more not popular, but more studies talking on that. I'm thinking this can be kind of a breaking point to find out the real the mechanism of the formation. And if so, I mean, that would be very cool, because the ZDDP has this physical adsorption and also this interaction, the chemical reaction, and too many factors can build. And if there's like a better model can really understand the reactions all involved, then I mean, that can really solve the problem, how it is really formed on the surface. So it's a really quick comment. So I hope this can be solved in the future.